As Par mentioned, I'm Brian Gold. I'm an engineering director here at Pure on the FlashBlade team, and I'm going to take you through our hardware architecture. Really what I want to get to, though, is the question that Par posed, which is the why. Right? We'll tell you what's in it. We'll tell you the moving parts, or really the non-moving parts in our system. But what I want to leave you with is why we built it this way. And so to start understanding that, we need to look a little bit at what problem we're trying to solve. Right? So as Par mentioned in the setup, we're attacking the file and object application space. And what we found talking to customers early on and definitely through our beta program is that these applications, they need scale, right? But they need scale in a bunch of different dimensions. They need scale in capacity, right? Where some applications are really fairly small, but they often grow to many, many petabytes. They need scale in concurrency. Sometimes you have a relatively small number of clients, small number of computers. Others, you have tens of thousands. And you need scale or really dynamic range in access patterns. Some applications are focused heavily on small metadata intensive operations. Others are large streaming IOs. And the really interesting ones are a bit of both. So what we need is to address scale, but we want to do that without drowning users or administrators in complexity. This is where we see in traditional file and object store architectures, we see a number of different patterns that emerge, and we believe that's largely due to the limitations of spinning disk. That the traditional assumption that you have to use spinning disk to achieve this scale in a cost-effective way leads vendors down a path of building very different architectures to solve different subdomains of this world. What that then leads to is complexity for the end user, because they have to either manage, they have a choice, either they manage a patchwork of different architecture for different parts of their problem domain, or worse, they choose one and then stretch it to its limits and then have to go implement caching layers and rewrite their applications to work around the inherent limitations in whatever they've chosen. And so we want something that achieves a broader scale without this complexity. So let's make this a little bit more concrete. What would we get today if we were deploying a typical kind of scale-out NAS array? Well, like I said, we start with disks. We put a bunch of them in because they're cheap. Of course, spinning disks, you can't directly attach them to a CPU, so you need some kind of a host adapter. Disks are slow, so we put a flash cache in. We probably need some kind of an NVRAM device to buffer and provide stable storage for writes. Finally, we can actually put a CPU and some DRAM. We've put all this other stuff in, so we might as well put another CPU, like a dual socket system. We probably designed this 10 or 15 years ago, so we've got separate networks for external client-facing traffic and internal messaging between the scale-out nodes. Put the whole thing in a 1RU box, scale it out, and this is what you get. Right, this is an actual deployment. The vendor's very proud, and the operational team should be very proud for making this work. It's incredibly complex to deploy, maintain, and manage something at this scale. Right? So let's rethink this a bit. What is it we actually want? From a hardware perspective, we need storage, we need compute, because we're building a file system, an object store. There's quite a bit of computation required, and we need really fast networking. Right? So clearly, what we should do is do a bunch of 1RU servers and put giant SSDs in, right? Well, we're going to end right back up here, because we still have a connectivity problem if we want to hit scale, and we're basing this on 1RU servers.
Hey, Brian, what's that?
We know this because we built this. The image on the left here is our first prototypes that we built. So we had a problem. We're doing both hardware and software development. We started them together, and so we built using commodity hardware, we bootstrapped our software development such that we could start working on all the things Rob is going to talk about in a distributed file system and all the optimizations we wanted to do. And the connectivity on the back, it starts to look like this. Right, so we don't feel like that's a great solution to the overall complexity problem that we're going to end up if we want to hit this scale. And furthermore, we could go the opposite extreme. We could say, let's take a 4U box, let's cram as much flash in, let's cram computers into it. But now you have a giant failure domain. You may not even have enough compute that you've put in the box. What we really need is a modular architecture that integrates a lot more of the networking. And so, there's a pretty good solution to this, which is blade chassis, which are relatively unused in the storage world, but are widely deployed in the compute farm world. And so this, as you've seen, this is our overall chassis structure. But let's get to what's inside of it. We've got the demo units over here that you can see. What's actually inside of this thing? Let's start by looking at the networking aspects. What have we done to integrate networking into the system? So the module that PAR is holding here, it's effectively a top-of-rack network switch. We use basically the standard, de facto standard switch ASIC chip there. That's the large copper heat, under the large copper heatsink. And we've collapsed the networking infrastructure directly into our chassis. What that allows us to do by using a modern high-performance fabric is we get to take advantage of all the software-defined networking features that have been implemented and that switch vendors like to tout. Well, there's actually a really good use for them in our application because we can collapse 3 separate networks. We can collapse external client-facing traffic on the front end, back-end messaging between our server nodes, between our blades, and control traffic. All of that can sit on the same really high-performance fabric. It simplifies even our internal structure tremendously. We can provide a lot of uplink bandwidth using in the total chassis. So we have 2 of these modules for redundancy. So you get a total of 8 40 gig. It's standard QSFP Ethernet. Using Ethernet was a very conscious choice on our part. We wanted to make use of the most widely deployed network technology available. We know the roadmap for Ethernet is very strong in terms of its technology scaling. And it's essentially solves how we scale out beyond a chassis. At a hardware level, it's effectively a solved problem. You can deploy a larger switch sort of to aggregate multiple chassis together, and we can achieve scale from a hardware perspective in a fairly straightforward manner. On that fabric module, that's our term for this switch, there's also a computer, there's a server that provides chassis management, the control path for the overall enclosure, but it doesn't handle any of the I/O. All the actual data path passes straight through the networking plane and into the blades themselves. So let's talk about the blades. And to do that, we'll sort of pivot and go to a bit more of an architectural block diagram. Inside the chassis, we have these network switches that we've talked about. And then the blades, from a compute point of view, it's fairly straightforward. We built a computer. We put it in a blade form factor, but it's a standard Intel server with DRAM and integrated networking to connect up to the fabric. If we stopped here, there's really not that much sophisticated to it. It's maybe a nice packaging, nice modular form factor, but nothing really that different. And frankly, I don't think you guys came here today to hear me talk about how we've integrated fans and power supplies. So let's talk about the flash and the NVRAM, the custom hardware that we've built that's attached into each one of these blades. So this is where I really want to get into the depths of why did we build it this way. And to answer that, we need to step back and look a little bit at what's in an SSD today. Why didn't we just put 16 terabyte SSDs in this thing and declare a density record and be done? Why did we do this custom stuff? So what's in an SSD? Well, for most of us, it's basically a black box. It has whatever interface you choose, whether it's a legacy storage interface or a more modern interface. You have a fairly simple logical access protocol. I can read, I can write, I can trim, and the machinery inside is opaque to me. Inside, though, the SSD has to solve really 2 key problems that I want to walk you through. First is, how do we do I/O scheduling and data placement, right? When we do writes, we have to decide, the SSD has to decide where should that write go on the flash. And the second problem is the flash translation that has to occur and the wear leveling that has to occur due to how flash works internally. And some of you may have seen some of this from other vendors or technology briefings. I'm going to give a real quick primer and sort of quickly, hopefully, get to the insights that we have and how we think about where this implications on our system. So let's take each of these 2 challenges in turn. First, the I/O scheduling problem, right? So we're gonna peek inside the SSD now. So we still have our traditional interface there on the left, but if we go all the way down to the smallest granule in the flash, flash is a fairly unreliable medium. I think that's widely known, right? We have to have sophisticated encoding, and we add parity bits when we write the data to flash, to the media, such that on a readback we can correct bit errors that may have occurred. So we have some unit of encoding. It's typically 1 to 2 kilobytes in a modern SSD. And that's the small, we can't really peek inside the data below that. That's our code word. We'll pack multiple code words into what's called a page. That's the smallest unit, and this is dictated by the flash geometry itself. That's the smallest unit we can read or write. And so each page will have some number of code words. A page today is typically 8 to 16 kilobytes in size. Multiple pages get consolidated into an erase block. That's the unit at which we erase. As you may know, Flash, you have to erase it before you can then write it, and you have to write pages sequentially within the erase block. There are basically all these rules of the road to make use of the technology. Multiple blocks get aggregated into a flash LUN. This is different than a SCSI LUN. It has its own terminology. This is inside the flash. The LUN is a unit, a logical unit is what we can have one outstanding access to. So it's a unit of concurrency. You get multiple LUNs go into a die, multiple die may go into a chip. I got lazy and stopped drawing the rectangles. It was so complicated. And then multiple chips will go onto a channel. A channel still inside the drive is our unit of transfer. We can only have one thing. It's a bus. We can only have one thing on the bus at a time. And we'll have multiple channels inside of a single SSD. The point of all this is to show you there's this kind of Russian stacking dolls, if you will, of the internal geometry within the SSD. And it's the job of the firmware inside the drive to make use of all the inherent parallelism while navigating the rules of the road. And it has to do that with essentially no knowledge of the application all the way up the stack. It's got that thin straw that it can see through. And we can put faster wires attached to that, but we're still condensing things down to 4 kilobyte, 16 kilobyte, 32 kilobyte block IOs. So that's problem number one. Problem number two is actually somewhat related. It's flash translation. So we have a traditional SSD will present a simple logical sector address that we've had for a long time in storage. Today, typically 4 kilobyte minimum sector size. The flash, as we just saw, has this incredibly complex geometry underneath. And so there has to be some mapping from simple logical space to rather complex flash geometry. And like all problems in computer science, this is solved with a layer of indirection and done through a flash translation through a metadata mapping layer. So we have to have some metadata that we keep, and typically this is cached in DRAM inside the SSD. The computation to do that translation is often done in embedded processors. You'll find embedded ARM cores inside of most SSDs. And as we start to want to scale how much flash we attach, now we start running into problems. As we scale that flash to really, really big sizes, we have to scale that metadata. That's a fundamental problem. However you want to structure this, you have to scale that metadata. You have to scale how you access that metadata. That means more DRAM, more compute has to be inside the SSD so we can preserve this rather simple abstraction. So you might say, wait a minute, there are 16 terabyte SSDs available today. What's the, clearly this is a solved problem. That's true. But what the problem we're highlighting here is fundamental to what you have to do inside the drive. You have to bring more DRAM and more compute to the metadata problem. And so So
Brian, are you implying that in the way that traditional drives went to a position where we got lots and lots of capacity, but we didn't necessarily get additional performance out of it? Are you saying that flash SSDs, as they go to 16 terabytes and above, are going to go down that similar route where we'll get lots of capacity, but we might not necessarily see a significant increase in performance for those devices?
So that's a great question. We may see some of that, but the other trade-off that could be made is let's increase the amount of computation and DRAM, the resources we put into the problem to achieve that performance scaling. That's why I say it's a fairly fundamental problem, because you have to pick some side of that trade-off in which to live.
Okay, so does that mean the drives could get, obviously there's a cost to that, I would imagine, but also does that then affect things like power and cooling? Are the drives going to run with more energy?
It all depends on the implementation choices. Okay. And that's really the key point that I want to get to, is you have a choice. As an architect, you now have a choice. And it's the same problem we face in lots of parts of computing. We need, if we want to keep performance scaling going, we either scale out or we scale up, because we have to bring more resources to the problem. If we scale out, we're partitioning something. We're going to partition this space up. We'll have maybe inside the SSD, we might have multiple controllers, and we'll wrap it all up and you won't know that we have that going on, but under the covers it gets really complicated and there are implications for that. Or we can effectively bring a server class CPU and DRAM resources to bear on this and scale up. Right? But one side of that, or we give up on performance scaling. Our belief is that some part of that has to be done. I can't tell you, I don't know what the commercial vendors are doing and where that'll go. I suspect you'll see some of all of these things get tried because there's a hard problem here. Yeah,
the reason you need more computers because you're doing more IOPS per unit, is that? If
you want to do that, and even somewhat to maintain this, you have larger structures. You have a larger search. It's a search problem. And as you do writes, you have a larger space over which to find free space, over which to garbage collect. Right. So even without necessarily scaling performance, you still have a scaling problem to just in terms of capacity.
Structure scales incur some sort of compute overhead to manage and.
Yeah.
It's directly correlated, right?
Yeah, fairly. The details are always. I'm simplifying a little bit, but
I understand.
That's the problem that we see. So, however, I claim this problem is fundamental to working with Flash. We are clearly working with Flash. So what's our solution to this problem? And I like the saying of if you can't win the game, change the rules, right? So why would we put a logical sector address interface on our drive if we don't have to? And so let's take a look a little bit. I'm going to quickly walk through what's in that typical SSD controller. I'll come back to some of these other blocks, but really what I want to highlight is the problem we've seen is it's this flash translation that we're doing inside the drive. Presenting that logical sector addressing model and then mapping it down to the underlying flash, that's preventing parallelism in how we do scheduling because the application has no idea what's going on under the covers, and it's limiting our ability to scale capacity. And so the question we asked is, well, can we just get rid of it? Can we not do the flash translation, at least not in the drive or our storage module? And the real insight here that we think we've had, and maybe others have had as well, is let's give array levels. We are not a drive. We are a system. So let's give control over how we do this data placement, scheduling. And let's make that underlying architecture very visible to the overall software that's in our system. And we came upon this really out of experience from building FlashArray. And I think this is true of lots of other software systems that have worked with SSDs today. You could go find, I think you'd find the same thing looking at, say, RocksDB, a key value store optimized for SSDs. You end up building a lot of structures that are tuned. Even if you don't know what's going on in the flash, you know the basic properties of it. And so you implement log-structured data storage systems in application-level software to work with the basic requirements of Flash. Well, if you're already going to do that, we're basically prepared. We're implementing a Flash translation layer, and we've talked for years in FlashArray and as part of our Purity software system of we've implemented a Flash personality layer. So we are already doing that in software. In some respects, what we're arguing is let's just do less work. And that's really the key insight we had and led us down the path of building a custom module. Is our custom module looks roughly like this. It has the key data path parts. It has a highly efficient PCI Express transfer. It has a state-of-the-art error correction codes, AES for encryption. It speaks the physical layer to multiple different Flash technologies. It has all those pieces that you'd find in an SSD. We've really just gotten rid of things. Now, we implemented it in a very flexible FPGA. You've seen other storage vendors have worked with FPGAs in the past. That just gives us a tremendous agility to work with different Flash technologies as they become available. But at the end of the day, what we found through our development and experiments is we get two things out of all this. We get a very scalable in terms of capacity storage module. So today, we're building 8 and 16 terabyte storage modules. Our original prototypes, I don't think we brought one. We did. So we built an initial prototype. It was actually just a little bit bigger than a hard drive. So it's done as a sandwich stack of boards. There's a controller board, and then and it says non-functional on the back. We're good. So there's 2 boards of flash. That's 8 terabytes. 8 terabyte storage module.
This is 2.5 years ago or so.
Right? So we get to 16 by just putting more dense flash down, right? It's the same physical structure. And because we've removed this flash translation layer and the way we've built the rest of the entire architecture is all designed to ride the scaling wave that's happening in the underlying NAND.
And this is what we put in a 1U server that we built?
Yeah, that orange 1RU box, it actually was meant to house that, to bootstrap the software development.
So initially, were you just thinking of building your own drives almost? Because it looks like the form factor of a drive. And
that's a great question. I'll take you through a little bit of our thinking. We very early on believed that we wanted to get to this blade chassis. But we knew that that was a lot of work. And we started this project, and some of this has been reported on it. We were a stealth mode startup within Pure. Those orange boxes that were shown, they didn't say Pure Storage on them. We actually wanted to be able to put them, and we did put them in customer data centers, and we didn't want people to know what we were working on. And so to give us flexibility and kind of modularity, we didn't know the right ratio of how much flash should we put with how much compute. We had to build a modular block that would allow us to do different experiments internally and find that right balance. And so we never thought about I don't believe we ever thought about going down the path of building a drive as a product. We always wanted to be in a full system.
Yeah, I guess I wasn't thinking of it as a product. I was thinking it looks like a drive, and was it just from a modular perspective
that was
easier to build it like that?
We couldn't mount it in a commercial chassis, and software had to get started before the hardware was ready.
Yeah. Okay.
So we had to have our software developers developing against something.
Something, yeah.
Yep. All right.
Software guys, always
So-
need something.
We've talked about our blade enclosure. We've talked about this incredibly scalable, high performance flash module. Arguably we could stop there, but we didn't. Right? There's one more problem that I want to talk about, one more challenge and an aspect of our architecture I want to talk about, and that's NVRAM. So if we return back to what's inside an SSD, I mentioned that the flash page is the unit of writing. We can't write smaller than that. It's about 16 kilobytes in many flash technologies today. So if I have a very small write, say a single byte write that comes in from a client, I don't want to burn a whole page just to handle that write. And so what basically every SSD today does is implement some amount of buffering that's typically held up in a consumer SSD. It's held up by ordinary capacitors. Enterprise SSDs will afford a little bit more energy reserves, batteries or supercaps to buffer a little bit more. Right? And you're getting not just the ability to buffer and match a little bit better the flash page. What you really want to get is coalescing of data and kind of almost reordering or laying out of data so we get better locality on the read path. If I've got multiple writes from a file that's interleaved with maybe some other write stream to another file, I'd like to sort of deinterlace those so that on the read back path, I've got all my bits coming together. And so that's one way we want to make use of NVRAM in any storage system. Well, in a consumer environment or in a direct attached server environment where I have a single SSD, I probably have relatively few concurrent write streams, 10 or fewer concurrent independent write streams. And so I don't need a lot of buffering. But in a large scale storage array that's designed to hit thousands of concurrent clients, hammering away on our storage system, we need a lot more buffering to be able to do that deinterlacing. And we found this to be really important in real world applications where we have lots of overwrites maybe going to the same file, where if you write a certain piece of a file and then overwrite that same file, we don't even need to write that original data out to flash. We can elide it or coalesce it directly in NVRAM, where access is extremely fast and we don't have any endurance issues. So there's a lot of very real-world benefit from having a high-capacity NVRAM. So how did we implement that? Well, we have this custom module. We have a lot of flash. We implemented it in some respects by taking all that DRAM we're not spending on building a flash translation layer and converting it to NVRAM. And so we can, with well-understood technology in terms of supercaps, we can attach gigabytes of NVRAM into each one of those storage modules. And so the thing that's getting passed around has the little white, those are white modules, those are supercaps that provide enough holdup to flush several gigabytes of DRAM out to flash in the event of a power outage. So we could have stopped there and said, all right, we've got gigabytes of NVRAM and we've got lots of flash, but there's one more piece to this, and this is really...
Gigabytes of NVRAM per flash module?
Yep.
Yes.
You got 10,000 write streams, it's incredibly beneficial.
Per flash module?
Yep.
Our flash module.
And so I love the face.
You have 4, right?
I love that look.
4 gigabytes in the
We
module you
worked
held in your hand.
really hard to do that. So I love that look of incredulity. We found that to be just enormously beneficial. And we've done experiments where we vary the amount of NVRAM we dedicate. And as you add more and more clients and more write streams to that, that ability to de-interlace those streams becomes very, very powerful.
Can you theoretically do it again? So in the next generation of the product, so all the pieces that you are seeing are tunables or not? If something changes in the layout of NAND or whatever.
Great question. So how do we adapt to future technologies? There's a couple of things that I want to point out around that. The first is much of what we did was actually remove things out of the SSD. There's a lot of the work that goes into building an SSD is implementing that flash translation layer. So our observation of, well, we're already going to be doing that in software, as we do today in FlashArray, it really allows us to play to our strengths as a company, which is doing that software development. It means we're doing less in the drive, and there's less. So a new flash technology, we're really adapting sort of how we do encoding, somewhat how we do signaling, although that's fairly steady these days. And the rest of these blocks are fairly standard. And the whole thing, we've implemented it in an FPGA, which gives us that adaptability. We're not doing a new silicon spin every generation. And so we've already, in our prototype phase, before we even go to full production, we're using 2 wildly different flash technologies for our different sizes.
You told us that you built a startup, stealth startup into your startup, okay?
Yep.
So, but how much of the knowledge that you had on the FlashArray was, transferred to this new startup? Because when we met at the launch of the product, you said you had just a different team. So
the engineers were different, but Pure is an incredibly open, transparent company internally, and so we had, a lot of it is more about lessons learned than particular pieces of technology. It's all the sort of institutional knowledge you get from 7 years of building the FlashArray product. That's really what transferred. We did, and Rob will talk a bit more about this. We did actually borrow some code too that has to do with how you lay sort of data structures of how you lay things out. But really, what matters is the institutional knowledge that gets built in how you work with Flash. So there's one more piece of this, which I can only give a little bit of a teaser. It needs more context that Rob will give as far as how we implement a distributed file system. In a scale-out architecture, often the Achilles heel of especially small metadata-focused applications, the Achilles heel is how do we do coordination at scale? And this is essentially the same problem as distributed transactions in a scale-out database. And so it turns out NVRAM is really critical for that. We need to be able to write down little pieces of information. If we're moving a directory from one part of a namespace to another, and we have to coordinate that across the different servers in our system, we have lots of little pieces of information we need to write down. And so we've got a really optimized software protocol that Rob will go through. But once we've done that software optimization, there's still, even with fast NVRAM, there's a lot of software work that was left to be done to actually ensure atomicity in how we persisted things. And so we just moved that into hardware, right? We have all these pieces. It's actually a small part of our implementation, but in some ways it's the most critical last piece of the puzzle to achieve scale for file system metadata intensive applications at scale. And so I'll leave a little bit of a teaser for the details to come from Rob, but that's the last piece of key architecture that we put in how we built this custom module.
Can I ask a quick question?
Yep.
You talked about the networking module. You showed us that. How do the blades actually fit into the back of that and connect? And
yeah,
what's the interface there? Because I think we really sort of touched on that in detail.
So great question, and I've got a picture on this coming up, but I'll just show and tell here since you asked. So this is the 52 terabyte blade. The green boards here are the flash. There are actually 3 of these storage modules. It still, even though it's gone to a planar card, it's still logically a modular unit the way we started. And then this red board in the back here is the computer. It's a Intel CPU, DRAM, and then the connections into that switch fabric are done through a mid-plane. And so the overall enclosure, the entire chassis is a modular chassis. Right? This is a field replaceable unit. In production, there's a cover on the top.
So where's it getting power from? Or is it plugging into both of them? There's two,
Yep.
one for the top, one for the bottom. But is it taking power as well as the
Yep.
networking from that connector all in one?
Yeah, there's a connector down at the bottom that provides
Okay.
the power, and there are 4 power supplies
Along the bottom.
along the bottom. So it's redundant power, and then you've got redundant networking.
And it's really eight connection in total, 8 lanes to every blade, 4 from each of the fabric modules.
Yep. And so that's a great segue into kind of how let's move back up the stack, basically. We've talked about this building block, this storage module. You know, we've built this as, for example, in an 8 terabyte storage unit, we can attach back into the server CPU we're using. Intel has recently launched a system on a chip called Xeon D. So it's a server class CPU, but it's got integrated networking. So it fits really well with our density. And it's got server class amounts of DRAM. We can also double the density of the NAND itself to hit a 16 terabyte storage module. And we can put 3 of them, which is what I was showing. And that's how we get to the 52 terabyte blade. And then pictorially, and I think you can find pictures of this online as well. This is kind of the same walkthrough. There's the storage module, the FPGA controller and flash, DRAM, supercapacitors. You're asking about the amount of NVRAM we put. The original prototype that Chris is holding, you'll notice only has 2 of the supercaps, and the boards here have a lot more. And the reason for that is we did experiments and found just how beneficial it was for performance to have more NVRAM. More NVRAM needs more hold-up time, so we put more supercaps down, all through experimentation.
So was that did you get to a point of diminishing returns where you suddenly thought, we're not getting anything extra now, we've got to a
The
level
bottleneck shifts elsewhere,
Yeah.
and we go and attack that, which is how we ended up with this clever transaction engine in hardware. It's sort of, performance is always a bit of a, find the low-hanging fruit, pick it, and then move to the next lowest hanging fruit. So, I hope I've thrown a lot of content at you. I hope it made sense, but I really hope that you take 3 things away from the hardware section of our talk today. The first key takeaway is that we've built this integrated blade chassis to provide density and really simplicity of deployment and management. The second is an all-flash storage unit that unlocks the parallelism and underlying capacity that we can get from the flash that's normally locked away inside an SSD. And the third is, and forgive me, I have to get some of the details from Rob, but the NVRAM engine that we built to provide large amounts of NVRAM and this distributed transaction processing acceleration that we get. Those are really what we think of as the 3 key things in our hardware architecture.